My name is Yarim. My research is an attempt to find a way to strategically inhibit beta-amyloid aggregation in the deadly Alzheimer's disease. Alzheimer's disease affects 80 million patients worldwide and is caused by amyloid plaques, as seen here. And these amyloid plaques are aggregations of beta-amyloid, a polypeptide. And here's the phenomenon in which these amyloid plaques are formed. So first, there's an APP, transmembrane protein, that is cut by secretase and forms this alpha helical structured amyloid. In Alzheimer's disease, this alpha helical structured amyloid misfolds into a beta sheet structured amyloid through various reasons. And this beta sheet structured amyloid is more vulnerable to lipophilic interactions, thus many of them come together and aggregate and form plaques, which eventually causes cell death. And the reason why these beta sheets come together and form these deadly plaques is because of a lipophilic interaction called pi stacking. Pi stacking generally occurs between two aromatic or phenyl rings, but specifically in Alzheimer's disease, pi stacking occurs when the amyloids aggregate together. And the reason why these amyloids are able to come together is because of two key phenylalanines in its sequence that allow for this pi stacking to occur. In my previous research, I used a peptide with pi stacking power in order to speculate aggregation ability. And so out of the various R groups that I attached, when I attached a fluorine, this peptide aggregated so much, which shows very strong pi stacking power and thus strong aggregation property. And so with this, I had a new idea, the idea of combating Alzheimer's disease in a chemical light. So using my stronger pi stacking mediator, I can better attract a weaker pi stacking beta amyloid, preventing that beta amyloid from coming together with another beta amyloid, halting the overall process of aggregation. So here is illustrated a beta amyloid aggregating with another beta amyloid makes this aggregation. This aggregation comes together with another aggregation and eventually forms this kind of plaque that we know as amyloid plaques. And so when I add my drug candidate into the picture, there's weak interactions between the beta amyloid than if my drug candidate was not there. And so this actually causes this beta amyloid to have random orientation and eventually form this kind of system, which is very unstable because of the weak lattice energy, and thus makes this whole system fall apart. And so in order to successfully terminate Alzheimer's disease, the target is this amyloid plaque. And in order to target these amyloid plaques, we must use strong pi stacking drug candidates. And so my general procedure of research is a repetitive scheme in which my goal is to make a drug candidate that can successfully stop aggregation. So first, I will synthesize a drug candidate and then test whether or not it has the potency to stop this aggregation. And then finally, I test whether or not it can actually stop amyloid plaque aggregation. And along the way, if I happen to fail, I will go back to modify my drug candidate in order to reach my goal. So my first drug candidate I called MEP1, and it was especially designed for its strong pi stacking power, as you can see with the modification of the fluorine group. And it was also especially designed for its lipophilicity so that if administered, it can safely travel through the blood-brain barrier. And finally, it was especially designed for its stability so that when administered orally, it can safely travel through the acidic and basic conditions of the digestive tract. So in order to synthesize MEP1, I did organic synthesis. So here's the synthetic methodology with Grignard reaction. So first, there's an alkyl halide in the presence of magnesium and ether in order to form a Grignard reagent. And as soon as this reagent forms, I add it to a diketone in hopes to form my drug candidate, MEP1. But unfortunately, instead of forming MEP1, I formed a byproduct. And the NMR confirmed for me at 2.8 ppm was a singlet signal that my byproduct was a dimer. So then I asked why and how did this dimer form? And in order to answer this question, I went back to the mechanism study. So first, there's an alkyl halide that reacts with the magnesium in order to form this Grignard reagent. And I deduced that as soon as this reagent forms, this partially negative carbon immediately attacks the reactant, thus forming this dimer byproduct. So then, in order to decrease this rate of dimerization, I wanted to get rid of the excess amount of this reactant. But after modifying my methodology, I was unsuccessful. But with this, I was able to figure out that it's not the methodology or the technicality issue, but rather the nature of this reactant itself. Bromine is such a great leaving group and thus promotes this rate of dimerization. So I wanted to use a more poor leaving group, such as chlorine, in order to decrease the rate of dimerization. So after modifying my methodology accordingly, the NMR confirmed for me at 2.8 ppm with 2 doublet signals that I successfully synthesized NAP1, my drug candidate. So after successfully synthesizing it, I went on to test if it actually has that strong high stacking power that I designed it for. And so here you see that this is the self-aggregation experiment using UV spectroscopy, and as the absorption increases, the aggregation increases. And by doing this experiment, I can see how well my drug candidate is able to attract a beta amyloid, stopping this aggregation from occurring. And so here is the NAP1 trend of aggregation, and it is definitely stronger than beta amyloid aggregation, so it does have the potency. And so I go on to test whether or not it can actually stop this aggregation. And when I add NAP1 to the beta amyloid solution, actually the beta amyloid and NAP1 complex does not really vary from just the beta amyloid aggregation, which shows that it's inefficient in stopping beta amyloid aggregation. And so I go back and ask, why did NAP1 not work? And I said, maybe because NAP1 was not having this optimal binding ability. So for my next drug candidate, NAP2, I wanted to add another fluorinated ring. As you can see here, it has very good binding ability to the actual beta amyloid aggregation. And so to synthesize this, I did organic synthesis once again with my modified methodology. And the NMR confirmed that I successfully synthesized it, and I went on to test the potency, which in fact it does have strong high stacking power, stronger than beta amyloid. And then I went on to test if it can actually stop this aggregation. But when I add NAP2 to the beta amyloid solution, it actually aggregates much more than just the beta amyloid, and that's not the direction that I want to go. It actually promotes aggregation rather than inhibit it. So I went back and asked, why did NAP2 not work? And I said, maybe because NAP2 and 1 were so lipophilic in nature and thus promotes the insolubility of the drug and beta amyloid complex. So for my next drug candidate, I wanted a more soluble drug candidate, such as peptide drugs. So this is my next drug candidate, PEP1, and it actually has a similar backbone structure as NAP2 and 2 fluorinated rings for strong high stacking power. And in order to synthesize PEP1, I used solid phase synthesis, and the product was injected into HPLC, which shows that there was a relatively pure product, and the mass spectrometry confirmed that the mass of the product was equivalent to the theoretical mass of PEP1. So I successfully synthesized PEP1. Then I go on to test the pi stacking power, which indeed it has strong pi stacking power. And finally, when I add PEP1 to the beta amyloid solution, it actually was very similar to NAP1. It wasn't very effective. And thus, I went back again and I asked, why did PEP1 not work after so many modifications? And I said, maybe because PEP1 is so short in length compared to the huge beta amyloids that it's trying to blockade between. So for my next drug candidate, I wanted to lengthen it. So I actually used beta amyloid 15 to 20, a clinically proven drug candidate, but I will add my special modification of the fluorine groups in order to have strong binding ability. So I synthesized with solid phase synthesis, and the HPLC mass spectrometry confirmed that I synthesized it. And the self-aggregation test indeed shows that it has strong high stacking power. And when I add PEP2 to the beta amyloid solution, the aggregation actually plateaus out, which shows that PEP2 is able to stop the aggregation of beta amyloid and thus pave a way to stop the progression of Alzheimer's disease. And so in conclusion, PP2 was very good in vitro, so I hope to work with it in vivo and hopefully in preclinical and clinical testing in the future. Also, in the future, when I want to work with it in clinical testing, there might be a necessity to have higher concentrations of this drug candidate. And that might be a problem because it has strong self-aggregation. So one solution that I came up with is using a blocker. So one example is this electron-rich phototrigger that will cause repelling of these two drug candidates. And another is a bulky group that will increase the steric hindrance of these two drug candidates. And through these ways, I hope to further work towards a way to stop the progression of Alzheimer's disease. And before I finish, I'd like to thank your college, the chemistry department, and Provost Malakidis for being so kind and giving me this opportunity to research. And to my teachers, Ms. Overlander and Mr. Perzio, who initiated my love and passion for science. And finally, to Dr. Profit, who showed me how important science research is to humanity. Thank you very much.